Welcome everyone. Uh, Let me start by mentioning a few routine details. Please keep your audio muted during the talk. However, if possible, keep your video on so that the speaker can see a few faces and it doesn't feel like talking to a PC. Please feel free to type clarification questions in the Zoom chat. I'll be monitoring the chat box. Once in a while, I may interrupt the speaker and convey the questions. In addition, there will be one or two short breaks during the talk when you can unmute yourself and ask the questions directly. Also, there will be a longer Q&A session at the end of the talk when you can ask questions as well. All right, so it's our pleasure to have Professor John Tsitsiklis from MIT today. I don't think John needs an introduction to this audience. In any case, let me mention a few words briefly. Professor John Tsitsiklis is currently a Clarence J. Lebel Professor of Electrical Engineering at MIT. After serving as acting director and co-associate director, he is currently the director of the Laboratory for Information and Decision Systems, LEADS at MIT. He has also served as co-director of the ORC at MIT. His research interests are very broad, spanning the areas of systems optimization, communication, control, and operations research. And he has co-authored 4 famous books. John has received several awards and accolades. He's a fellow of IEEE and of Informs. He's a member of the National Academy of Engineering and holds 3 honorary doctorates. Among other distinctions, he is a recipient of ACM Sigmatrix Achievement Award in 2016, the IEEE Control Systems Award in 2018, and the Informs von Neumann Theory Prize in 2018. So without further ado, let's welcome Professor Tsitsiklis. John, please go ahead.
Mm-hmm. Well, thank you for the invitation. Thanks to the entire team, Debankur, Wayna, Siva, Christina. So I'm going to talk about a topic that's a little bit esoteric and tangential, somewhat technical, but it was a technical question that was bothering me for some time. And with apologies to a few people maybe in this audience that have heard a version of this talk, but I think that most people haven't. I haven't spoken about it too often. So this is work that was done primarily with Arsalan Sharifnassab. He was a visiting student at MIT for a year, and during that year he did lots and lots of great research, and in particular I gave him an open problem that I had in mind and that's related to this talk, and very quickly figured out how to deal with it. And Jamal Golestani, who's actually a Leeds graduate, is Arsalan's thesis advisor in Iran. Now, normally, co-authors are invited to participate in the chat and answer questions in real time. And it's a really sad state of affairs that because of so-called export control laws, in fact, he's not allowed to participate. So it's quite a shame that we have such obstacles in international collaborations. But I'll leave it there. So the topic is about max weight dynamics. And so I will try to make the talk accessible even those who are not deeply into the technical parts of this topic. I'm going to describe the max weight policy and a few things that we know about it. Then I will pose the question of interest. And we will see that in order to address the question of interest, it actually helps to think about it more broadly in terms of a broader class of dynamical systems and some qualitative properties that they may have. And once we get a general theorem for that class of systems, we're going to go back to max weight and specialize. And the main point will be that using this tool, at least for max weight, the difficult results that people have been proving turn out to be easy, low-hanging fruit after you develop the right machinery. And I will conclude with a few generalizations and questions. All right, so what is the MaxWeight policy? Let's look at a very simple situation where we have two incoming streams of jobs, and they go into a queue, and both of them, they have rates lambda1 and lambda2, and you have a server that works at unit rate. So this system is going to be stable as long as the total incoming rate is less than 1, which is the capacity of the server. And as long as you do something reasonable, you can keep the system stable. And one way of keeping the system stable is each time that a job comes, you can flip a coin and serve the ith queue with probability. Well, no. At each time that the server is idle, you choose which queue to serve, and you choose which queue to serve with certain probabilities. As long as the probability of looking at a particular queue is bigger than the arrival rate of that queue, then both queues are stable. So that's a simple open loop policy that works, and you can do it with coin flips. But if you guessed the wrong arrival rates, this is going to be unstable. That is, if lambda1 is 0.6, but you flip a coin with probability 0.4, then it doesn't get enough service and it's unstable. So one needs a policy that actually looks at the state of the queues, and a very simple policy would be to serve the longest queue, and that policy is going to be stable as long as the arrival rate is less than the service rate. Okay, how can we... So it's a reasonable policy, but what's a way of thinking about it? One way to think about it is that we have a Lyapunov function that looks at the sizes of the queues, takes the sum of the squares of the two queues, and one way of thinking about it is that you serve Q1 if the value of the Lyapunov function at the next time, okay, there should be a subscript 1 here. If I serve Q1, next time my Lyapunov function will be this. If I serve Q2, the Lyapunov function will be this. And I choose to serve Q1 if the Lyapunov function will end up being smaller than what it would have been if you were serving the other queue. So what's the recipe that's involved here? The recipe is that you choose the action that causes the biggest reduction in the Lyapunov function. So you have a Lyapunov function, you ask how is it going to change for each one of the possible actions I might take, and take the action that leads to the biggest reduction. And this criterion here about the reduction of the Lyapunov function after you do the algebra and you cancel various terms ends up being just the policy of serving the longest queue. All right, so we can think in terms of Lyapunov functions. Let us now generalize this idea to come up with a MaxWeight type policy in a more general setting. Suppose that we have 3 streams and 3 corresponding queues. And suppose that the rules of the game are that at any point in time, you can serve 2 of the queues, but not all 3 simultaneously. So effectively, you can have a total service rate of 2. And as long as the total arrival rate is less than 2, then there are things that you can do and keep the system stable. Now, we could use the same idea, the coin flipping idea that I mentioned before, which is to choose certain fractions of the time that you serve different queues. So for example, fraction of the time F1, 2, you might choose to serve queues 1 and 2. And the fraction of time you choose to serve queues 1 and 3. The sum of these is the fraction of time that you're serving Q1. As long as this is bigger than the arrival rate of Q1, then Q1 will be stabilized. And you have similar condition for all 3 queues. And you look at that system of inequalities. As long as the total arrival rate is less than 2, this system of inequalities will have a solution, and using that solution, you can stabilize the system. So coin flipping again works. So that would be an open loop policy. But again, if you don't know the lambdas, it could easily become unstable. So we need something a little more clever. What is it? Okay, so let's introduce some notation. We have different service vectors, which we call schedules. One schedule is, so the schedule is what do you do at any given point in time. One choice that you have is to serve queues 1 and 2. Another is to serve queues 1 and 3. Another is to serve queues 2 and 3. So in this example, we have 3 possible schedules. And we're going to look again at the same quadratic Lyapunov function as before, the sum of the squares. And the rule that we're going to use is to pick that particular schedule under which the Lyapunov function, after we apply the schedule, so after we apply the schedule, the Q gets reduced by the corresponding vector that we have here. So this is the Lyapunov function next time. And we choose the schedule that results in the smallest possible Lyapunov function at the next time. So removing the term that Q squared that does not involve sigma, we're left with this maximization here with respect to sigmas. And then we're mostly interested in the cases where the Q's might become too large. What should we do? In those cases, this would be the dominant term. So we can just ignore this term and just maximize this quantity. And maximizing that quantity, that's the rule that we're going to use. And that's basically the MaxWeight policy. For any schedule sigma, we defined the weight of that schedule to be the inner product of the Q sizes with the schedule. That's the weight of the schedule. And we choose a schedule that results in the biggest, that has the largest weight. And when you do the algebra, this translates to the following. I'm going to choose schedule that serves Qs 1 and 2 if the total weight of these two Qs, this is just the inner product of the Q vector with this sigma vector. If this is bigger than that and bigger than that, then you choose that particular schedule. So each schedule has each candidate schedule has a weight, and we apply the schedule that has the largest weight. And that's the MaxWeight policy for that particular example. So the MaxWeight policy was introduced and studied in a seminal famous paper by Tsitsiklis and Ephremidis. And more generally, it goes as follows. We have our queuing system, we have a Q vector, and we have a finite set of possible schedule vectors. These are non-negative, but they could also be fractional. They don't have to be integers necessarily. So for example, maybe this is a schedule in which we serve Q, the second Q at rate 1, and we serve the fourth Q at rate 2. So that would be an admissible schedule, for example, if we had 4 Qs. And for technical conditions, we assume that whenever a schedule is possible, we are allowed to replace some entries and make them zeros. That should also be an admissible schedule. That is, if you can do something, you can also do anything less than that. So that's just a technical condition somewhere. And the MaxWeight policy is this one. You look at all schedules. For each schedule, you look at the weight of that schedule, and you choose the particular schedule that has the least weight. Now, this would be what you do in single hop networks, where you serve a queue and then the job goes away. A generalization would be if you have a multi-hop network. So suppose that whenever you serve from this queue, then once the job gets served, with some probability, it might go to another queue. And we're told what those probabilities are. It's part of the model that whenever you serve Qj, the job might go away, or it might be sent to another queue, and that happens with probability Rij. So those R's together form a routing matrix. And so that will be the generalization of the dynamics in the multi-hop setting. So this routing matrix is just a non-negative matrix. We don't need to make more assumptions on this. And the dynamics then would be of this form. The Q vector at the next time is the current Q vector plus whatever arrivals have happened. This is a vector that tells us the arrivals at the different queues. And then you subtract how much was served. So how much is served is the vector sigma. But if it turns out that sigma is bigger, some component of sigma is bigger than the corresponding component of Q, you cannot serve more than what you have. So there's the minimum here. You serve sigma, but up to whatever you have in the queues, not more than that. So you subtract this. On the other hand, whatever gets served, the routing matrix sends it to new queues. And so we get an extra additive term from this. This corresponds to jobs that have been served, but are being sent to a new queue. So these are the dynamics. And how, and in the case that we have a routing matrix, we need to modify the choice of how we select our service. We look at the weight of the queue is how much we are removing from the queues, but also taking into account how much we're adding to other queues. So this is the net removal from the queues if we use schedule sigma, and that's the weight of a particular schedule, and we pick the one schedule for which this quantity is biggest. All right, what do we know about this policy? Let's look at the simple case where we don't have routing. As long as there exists some fractions with which you can use the different schedules and the total service at each queue is bigger than the arrival rate at that queue, and if this is true for all possible queues, then you can use those fractions and in an open loop policy and stabilize the system. And this is also, this condition is sufficient for stabilization, and it's also necessary, but I'm putting quotes around the if and only if, because if you are just satisfying the constraints, then you have a situation of marginal stability, and then things could go either way. But as long as you can satisfy this with a strict inequality, you can stabilize, and that's essentially necessary. So this is the seminal result of Tassioulas and Ephremidis, that you can stabilize the system. And the argument goes by using exactly that same quadratic Lyapunov function that I introduced before. And a similar property is also known for the multi-hop case as well. And essentially it says that whenever the system can be stabilized, the MaxWeight policy will stabilize it. And the wonderful property is that this works. It's a policy that doesn't need to know the actual arrival rate vector. So since then, there has been an enormous amount of research, maybe more than 1,000 papers or so, that analyze the MaxWeight policy, all kinds of things. People try to do performance analysis to say what are the resulting delays. That's a very hard problem. So one starts looking at scaling laws. As you get a bigger network, for example, or in the heavy traffic limit, you take all kinds of limits that you can think about and try to do a scaling analysis. And the results, one can look at generalizations, not only in the case where you have routing, given routing in the form of a given R matrices, but in the case where actually the controller can itself choose routes. Even for those cases, the system can be analyzed and one gets so-called back pressure policies and all that. All right, so now some key sets of results are that you can do a fluid limit analysis if you let the initial queues be very large and ask what is the system going to do. You can approximate the behavior of the system with a fluid limit. And basically what that says, let's look at a two-dimensional example. We have two queues. What the MaxWeight policy does is when one queue is big, you serve queue, so you tend to move in that direction. When you are here, you serve the other queue and you tend to move in that direction. And if you were to pretend that your system was deterministic, it would follow trajectories like this one. So it makes the two queues to be equal, and once they're equal, it keeps serving first the other, one queue, then the other, and so that it keeps the two queues being balanced. If you always keep serving the bigger queue, then you end up in a situation where the queues are approximately equal. That would be a deterministic version, but of course the real system is stochastic, and the trajectory that's followed by the real system is an approximation. The limit results basically tell you that approximately the stochastic curve can be well approximated a straight a curve that has straight segments. And the other results is about steady state collapse and state space collapse, which tells you that after enough time, the trajectory will end up hitting this line and will stay on that line, more or less, with small fluctuations. So that's the state space collapse type of result. So we want to look at these results from a somewhat new angle, and here's our viewpoint. We want to understand as much as possible as we can from a deterministic version of the system, understand the deterministic dynamics. So let's assume that arrivals come in a deterministic way. And then when we have stochastic arrivals, to think of the trajectories of the stochastic system as being just a perturbation of the deterministic system. It's a perturbation because the actual arrival process is not deterministic. It has some fluctuations, and those fluctuations perturb the deterministic trajectory and make it to be a more random one. So we want to understand as much as we can about the deterministic system, and then see how this translates into results for the stochastic system. Of course, this idea is old. I mean, the whole analysis using fluid models and all that, that's what it really has in mind. And there's all sorts of limiting results in that context. But those limiting results typically do not tell you something about the size of the fluctuations. So the fluctuations are caused by the fluctuations in the arrival rates. Fluctuations in the arrival rates result in fluctuations in the stochastic system, but the line of results available in the literature do not tell you how the fluctuations here translate to fluctuations in that process. And this is what we want to do. And once we understand that relation, then we can get more exact bounds and so on. Now, in order to do what we want to do, we need to capitalize on special properties that the deterministic system has. What are some special properties? As you see from this figure here, the deterministic system has dynamics that have a constant drift in some region. Then you enter another region and you have again a constant drift. So the state space is divided into a bunch of regions, and inside each one of the regions, the trajectories are straight lines. You're moving along a constant drift. So this piecewise constant drift is one property we're going to exploit. Another important property is that the max-weight deterministic dynamics are non-expansive. If you have a trajectory that starts here and another trajectory that starts there, the two trajectories move sort of in parallel, and the distance between the two trajectories does not change in time. At some point, they hit this line and both of them start moving downwards. As they start moving downwards, again, their distance does not increase with time. And that property is a critical one that we're going to capitalize on. All right, so we want to exploit this non-expansiveness property, for example. What does it buy us? Let us look more generally. What is a non-expansive deterministic system? It's a system that evolves according to certain dynamics and in which the mapping is non-expansive, meaning that the state of the system next time, starting from two different initial points, the distance between the next two states is no bigger than the distance of the initial states from which you started. Okay, what does this buy us? Consider now a perturbation of this system. You take that system and you add to it some perturbations, which might be stochastic, deterministic, of any type, and start the system from the same initial conditions. But one system is the unperturbed one, the other system is perturbed. So the trajectories of the two systems, even though they start the same, they're going to deviate. How much are they going to deviate? Well, each time the perturbed system gets hit by a noise term of this magnitude, and the total deviation is at most the sum of the amounts by which you get hit at each time. It's just the sum. You don't get any amplification factors, and that's where the non-expansiveness property comes in. So you get a hit from U at some time, and the eventual consequence of that hit does not get amplified. It's just this term. And then you add how many hits did you get, and that tells you the total discrepancy between the two trajectories. So, right, so what does this tell us? Suppose that the U's were random variables. You are taking magnitudes of those. So as you add them up, this will typically increase linearly with the number of terms that you have up there. On the other hand, suppose that we had a simple system of this type. This is a non-expansive system that moves with a constant drift. Then, if it's moving with a constant drift, the amount of hit that you're getting between the two trajectories, the perturbed trajectory minus the initial trajectory, you can calculate it in closed form, this is going to be the difference between the two trajectories. So the magnitude is going to be just the magnitude of this. And the important thing here is that we get the magnitude of the sum as opposed to the sum of the magnitudes. What does this buy us? If these are random variables, suppose they're kind of independent random variables, then typically the sum grows as the square root of time as opposed to linearly in time. And so that means that this term tends to be much smaller compared to other things that are happening. During a time interval of length t, there's things of this magnitude that are happening, but the effect of the perturbation is only this. So my claim is that for max weight dynamics, we have a behavior which is more of this type rather than that type. Why is that? Because in any given region, you have a constant drift. So in any given region, you're faced with such a situation. And so the perturbations add up in this way. Now, of course, things are more complicated because at some point you enter new regions and then nonlinear stuff starts to happen. And the question is, how does that nonlinear stuff impact the dynamics of the system? So what we wish to obtain is to show that even when we have those nonlinearities in the max weight dynamics, that we can still get the result of this type, that the discrepancy between the unperturbed and the perturbed system, that this discrepancy grows with the magnitude of the sum as opposed to the sum of the magnitudes. And once we have this is going to be a lower order term in a typical stochastic setting and will allow us to get results of various types. Now, it turns out that this is not an easy result to get. If we just have non-expansiveness in our dynamics, then you cannot show a property of this type. Somehow we need to combine the non-expansiveness property together with the piecewise constant drift property. And this is what we're going to do. All right, now let's start the somewhat more technical part of the talk. Let us see what the key ideas are. Let's ignore for a little bit I'm going to argue that the max weight dynamics are a subgradient flow for some particular Lyapunov function, not the quadratic Lyapunov function, but for another Lyapunov function. So let's ignore boundary effects for the moment. That is, okay, Q's cannot go negative, but let's forget about that. So we're looking at the deterministic dynamics, and in the deterministic dynamics, the change in the queues is the arrival rate plus, minus sigma star. Sigma star is the schedule that you're using, plus R sigma star, which is the effect of the routing. That's how things evolve. And our sigma star, according to the MaxWeight policy, is the following. It looks at the weight of schedule and maximizes this quantity. That's the MaxWeight policy. Okay, it looks at the reduction in the queues. This is the weight, inner product with the schedule. This is the weight of the schedule. We look at the schedule that has the largest weight. Okay, let me throw in here an extra term. I can do that because this extra term does not depend on sigma, so it does not change anything. And what does this correspond to? Let's look at this Lyapunov function. What is this Lyapunov function? Let's plot it as a function of Q. As a function of Q, it is something linear in Q, but then we take a bunch of linear functions. Each one of the linear functions is for a different sigma, and we're taking the maximum of those. So this phi is a function which is piecewise linear and convex. And it has finitely many pieces. Each one of the pieces corresponds to a different schedule. All right. Now, what is the subgradient? Oops. What is the subgradient of this? To find the subgradient of piecewise linear function, so the gradient at this point is you just take the gradient of this term. So you're taking the gradient of the maximize of this term, evaluated at the maximizing sigma. And the gradient of this with respect to sigma is just Q times, when you take the gradient, that Q goes away, you're left with 1 minus R sigma, that's this. When you take the gradient of this term, you get a lambda, and that's this. And you evaluate that gradient at the maximizing sigma. So the claim from this calculation is that the change in the Q is the an element of the subgradient vector of this Lyapunov function. So MaxWeight dynamics move, at least when you ignore the stochastic effects, they move in the direction of the subgradient of such a piecewise linear and convex function. So that's a key property we're going to capitalize on. And the analysis from here on is not really specific to the MaxWeight policy. It turned out that it's easier to think by just abstracting and looking in general at dynamical systems that are of this type. We have a dynamical system which moves in the direction of the negative subgradient. So we're going down in our Lyapunov function, and our Lyapunov function is a function that's, it has pieces, and each piece is linear in X, but we're taking the maximum of such pieces, and that makes it piecewise linear and convex. All right, so this is the class of systems we are studying. And I'm doing it in continuous time because the analysis makes a little more sense there. You don't have to deal with jumps, and then we will have to translate it in discrete time. Actually, it's better to think of those dynamics in terms of, instead of a differential formulation, in terms of an integral formulation. So Z is like the derivative at any given time. And the derivative is an element of the subgradient. and the state at some time t is where you started plus the integral of the derivatives that you have had until then. So this is just the integral version of this equation. So this is a deterministic, unperturbed system. This system, it's not hard to show from starting from these properties that it's a non-expansive, and it's guaranteed that solutions exist and solutions are unique. So these are fairly nice dynamical systems to work with. And now let's perturb our system. Instead of moving in the prescribed direction, we also have some noise terms. And again, it's better to think of this in an integral form. So the value of the state is the initial state plus whatever drift you had according to the deterministic derivatives, plus the cumulative perturbation you've had until then. So this capital U of t is supposed to be something like the integral of this little u. Among other things, this integral formulation is nicer because you can even talk about situations where this is Brownian motion, and which makes sense, but the derivative of Brownian motion would be a weird thing like a white noise. So if you think of U as white noise, we don't like dealing with white noises. We like to deal with integrals of white noise, in which case U of t would be just a Brownian motion. So here we've got an unperturbed system, and we've got a perturbed system. And the perturbed system is being hit by some perturbations, perhaps stochastic. And the result that we have for this class of systems is that the difference between the perturbed and the unperturbed trajectory is bounded by a constant times the magnitude of the cumulative perturbation. So this u, the cumulative perturbation, is like the integral of the little u's. So we're really dealing with a thing of this form, as opposed to having the absolute values inside. And for example, if this is Brownian motion, we know that this quantity is going to scale roughly like the square root of the time, not like the time. So this is the key central result on which everything rests. It's an inequality that's valid for a general class of nonlinear dynamical system. The proof is pretty horrendous. And the reviewers that looked at the paper basically said, oh, the proof is too complicated. There has to be a simple proof. Just find the simple Lyapunov function, whatever, and show the result. We believe that a simple proof does not exist, because if you make even small changes in any of the assumptions, the result is no longer true. So if phi is a convex function, but with infinitely many linear pieces, or a strongly convex function, a strictly convex function, anything like that, the result does not go through. And there are some very elaborate counterexamples that Arsalan has cooked up to show that. And so because the result is so sensitive into the combination of all the assumptions that are being made, a simple proof cannot exist, because if it existed, any simple proof would also work more generally. Okay, so how does the proof work? Here's the proof idea. As I said before, in one segment of, so since the system is subgradient of a piecewise linear function, means that the subgradient is piecewise constant. So you have regions of the state space in which you have a constant drift. Let's focus on the constant drift here in the vicinity of a boundary point between regions. It turns out for the systems that we're looking at, in the vicinity of a line that is somewhere between two regions, the drifts parallel to the line will have to be equal. That sort of comes out of the non-expansive properties for some reason. And the drift in the remaining n-1 dimensional subspace those drifts move in directions perpendicular to that line, and that lower dimensional system inherits the same non-expansive and piecewise constant properties of the original system. And that gives us the opportunity to use induction on dimension. That is, we decompose the system as a simple one plus a lower dimensional system. We make the induction hypothesis that the lower dimensional system satisfies the theorem, and then use that induction hypothesis to go up one dimension. Now, this picture is correct whenever you are near a line and you have an n-1 dimensional subspace orthogonal to that line. But once you get to a critical point, that is when many directions meet, then you cannot do that decomposition anymore. So you need a lot of special heavy lifting to describe exactly what happens in the vicinity of a critical point. All that is doable, takes a dozen pages or so, and that's basically how the result is done. But the key idea is this decomposition of the dynamics into two sort of separate pieces that can be analyzed. This one can be analyzed with first principles, and this is analyzed by using the induction hypothesis. And the fact that these two drifts are equal has to do with the non-expansive property of our system. Okay, so what do we get out of this? We look at the fluid solution for the MaxWeight dynamics. That's our unperturbed system. It's a deterministic system. And we look at the corresponding stochastic process. And we want to say something about their difference. They're different because the arrivals in the stochastic system are not that, but they are stochastic. They have fluctuations, and so they deviate from this. In addition, in order to talk about the MaxWeight policy, we need to take into account that when you hit zero, then you're not moving in the usual way, but you kind of have to stay on the boundary. And another complication is that our general theorem was in continuous time, whereas now the MaxWeight policy, I described it for you in discrete time. So there is a little bit of dirty work to be done but that dirty work is more routine. It's not as hard as the sort of big theorem. And that dirty work gives us, that's what the theorem is saying. The difference between the unperturbed system and the perturbed one is bounded by a constant times something that has to do with the cumulative deviation of the arrival process from the expected value or the deterministic arrivals. Remember, this A here is the instantaneous arrivals. So this sum is the total number of arrivals until time tau. Lambda tau is the deterministic total time of arrivals. So we're looking at the cumulative number of arrivals minus the expected cumulative value of the arrivals. We look at that quantity and see how big it gets within this time interval tau, and that's what bounds the deviation. Now, because when we deal with these terms here, some extra terms show up in our bounds, and that's what explains that we have to throw in a few other things there, but these things are just a constant, so they do not really change very much. Okay, and key point now is that if you make any reasonable type of assumptions on the arrival process, for example, if it's IID, bounded variances, things like that, this term here will evolve as order of square root t. Once you have that, then a fluid limit result is proved in just a few lines. You just make the assumption that the cumulative number of arrivals satisfies a strong law of large numbers. If it satisfies a strong law of large numbers, that is cumulative until time roughly n divided by n is the same as the expected value. And if you start the system from a large initial Q size, that's the scaling factor that comes in, then the scaled Qs over a time scale of order n, the scaled queues behave like the deterministic queues starting from q0, little q0. So this is the usual scaling that shows up in fluid limit results. And once you have this result here, this is just 2 lines of algebra. So basically, we've gotten rid of any sort of stochastic type of analysis by getting a deterministic result and then making just one light stochastic assumption and plugging that stochastic assumption into the bound that we had there. So given that we have a technology that seems to give results in a somewhat easy way, what can we do with this? So the next thing that people do in this field when they really want to exercise, to show their technical expertise, is to get state collapse results. So we're looking at a sequence of systems parameterized by a parameter n. So we have an arrival rate process for the nth system, and we assume that these converge to some, in a stochastic sense, to an arrival process for the limiting system, and the arrival rates converge to some limiting arrival rate. And we make the following assumption about how these systems behave. So the arrival rate process has some deviations from the average arrival rate. This is the stochastic arrival from the average arrival rate looked at over a time scale of n and then divided by n. The probability that this is bigger than some number, we assume that it goes to 0, and it goes to 0 according to this function. So think of taking that function, moving it to the other side. So you would get 1 over f of n delta there. That's the rate at which these probabilities decay. If you have a process that's kind of nicely behaved so that you can do large deviations analysis, then this term would be exponential. So the probability of large deviations would fall off at an exponential rate. That's one example. But we can make similar assumptions for other rates of decay of those probabilities. We do not need to assume that we are in the large deviations kind of setting. It could be other types of decay of these large deviations probabilities. Okay, now for the limiting system, there's going to be an invariant set. Suppose that the limiting system is such that, suppose we have 2 queues, the simple example, and in the limiting system, the sum of the arrival rates is 1, so the system is marginally stable. In that case, when the 2 queues, the state of the deterministic system does not change. The total service rate is the same as the arrival rate, and our policy keeps the state. If we are anywhere outside that set, what our policy does tends to equalize the queues. So starting from anywhere else, we tend to go to that invariant set. And once we are in that invariant set, then we stay on that set. So the fluid model has such an invariant set, and state space collapse results basically tell you that the stochastic trajectories will move to that invariant set and then start moving randomly inside that invariant set. So the formal version of those results would be as follows, that we look at a scaling of the Q vector. Scaling, we divide it by n, but we look at it over a long time scale. In this case, I'm taking a time scale of n squared. This is the so-called diffusion scaling. And the result under this assumption says that with high probability, over a time interval, t goes up to 1, so the actual time goes up to n squared. over a time interval of length n squared, the scaled Q stays uniformly close to the invariant set. And by uniformly close, I mean within a band. If you put an epsilon there, it would be an epsilon band around it. So this uniformly corresponds to this word here, that it's a strong state space collapse. There are other results that are weaker, so-called multiplicative state collapse, in which you stay inside the band that goes multiplicatively with Q. These would be bands that kind of open up as Q's go. The stronger result tells you that you stay uniformly close. It's a little technical difference, but actually going from weak results, state collapse, to strong state collapse usually takes a lot of sweat and a lot of effort. We get our results as a low-hanging fruit, actually, from our deterministic analysis, and just by invoking this assumption here. And we only need to invoke this assumption to get this result by assuming that this scales as n, so the probability of a large deviation scales just as 1 over n. We don't need it to be exponentially small. So it's a pretty weak assumption on the arrival process, and still under that weak stochastic assumption, we can get a strong state space collapse result. So a result of this type was conjectured in old work by Devavraj Shah and Wishik. Actually, that work was quite a bit before 2012, but it took a few years for the paper to actually get published. And in between, together with Yuan Zhong and a lot of sweat and trouble, we managed to show a strong state space collapse for the case of IID arrivals that were bounded. And because of the IID setting, you could be in a Markov process setting, and so you could use Lyapunov functions to carry out the proof. In our case, we don't need these strong assumptions. This result goes through with general arrival processes, and it goes through in a very simple way. You just make an assumption. Suppose I have a general arrival process for which large deviations have a probability that decays to 0 at some rate, and we get a strong state space collapse result. And we can get a strong state space collapse over longer time scales. If we are in the large deviations regime, it turns out that the state space collapse is valid over a time interval of length which is exponential in n. So we guarantee that we stay close to that invariant set for a much, much longer time scale. Is that useful for anything? I'm not so sure about that, but at least on the technical side, allowed us to kind of generalize and get as much as we could in this setting. So basically we found a hammer, a property of MaxWeight policies, and tried to see how much we can get out of it. How much does this thing generalize? Well, there are some easy generalizations. You can have weighted max weight, where different Qs have a different weight. It generalizes to back pressure policies when the routing strategy is no longer fixed. So you can do joint routing and scheduling. There's an open question whether we can get similar results for the MaxWeight alpha policy. Is it true that we have the same result, that it's only cumulative perturbations that matter or not? It does. The dynamics here tend to be more complicated. They're not piecewise linear anymore. So we leave that as an open question. How much in terms of similar results one can or cannot get for MaxWeight alpha? And finally, using this hammer, we can study some properties of MaxWeight policies under heavy-tailed arrivals. And that has to do with an old PhD thesis of a student I co-supervised, Michalis Markakis. We worked with Eitan Modiano and him, and we got some results for MaxWeight under heavy-tailed arrivals, but we left some open conjectures there they must be by now almost 10-year-old conjectures, or well, close to that. But we think that using this toolbox that we have in the talk I just gave, that we can figure those out. So with Arsalan, we're working on writing up those results as well. So this is all I wanted to cover. Thank you for listening. And these are the references.
Let's thank the speaker for the nice talk. So if you have any questions, please feel free to either type in the chat box or unmute yourself and ask the speaker. Yeah, Shiva, go ahead.
I have a few questions. John, thanks for the great talk. Does this result imply anything on the steady state bounds, the steady state behavior of the coulomb?
Yes, I always get that question. And the answer is that yes, with some work you can get steady state results, but they're not any stronger than existing steady state results. And the existing results that you have with Lyapunov functions actually have shorter proofs.
I see. But I don't see it. Like if I look at your main result on slide 13, you have this error going as square root of t, right? So as t goes to infinity, how do you kill it?
Yeah, so you would have to do the usual heavy lifting to argue that over a time period, some Lyapunov function will go down and then bootstrap. So it's essentially replicating the usual ways of proving steady state results.
One more question, if I may. Yeah. So the main result that you have about difference between the perturbed system and the fluid system being bounded by something that depends only on the randomness in the arrival, to me, it looks very similar to the Lindley's recursion in a single server queue. Can I think of this as the generalization of Lindley's recursion for a,
Yeah, that's a good point. I guess if you look at the single server queue and apply that result, that's what you get. I guess that would be for the single queue would be really like this. That's the deterministic system. Very simple case.
Correct.
Yes. And so for that one, of course, you expect that it's only the integral of the perturbations that matter. And that's what the recursion's done. Yeah, we hadn't thought of that, but I think it's a good point. Yes.
Okay. Okay. Cool. I don't know if there are more questions. Maybe I'll wait. I think there are more questions. I have a couple more questions. I don't want to.
Ruth has a question.
Yeah. Hi, John. Very, very nice talk. Very interesting. You mentioned multiplicative state space collapse. So I guess the point of that is that's all you need for a diffusion approximation. It's very nice that you can get strong state space collapse, but if your aim is to do the diffusion approximation, you just need multiplicative state space collapse, and it all kind of comes out in the wash then. So
yeah. Yes. So I'm not claiming that there's. I'm not sure to what extent that result that we got is useful for anything. It was just an effort to see how far can we go.
No, it's very nice. Yeah.
Probably, yes, for depending on your purposes, maybe doesn't add much.
Yeah. Thanks. Yeah.
So anyone else? Otherwise, Shiva, in the meantime, if you can go ahead for another question.
So one more question I have is about transient bounds. So I know that the state space collapse result that you presented is transient, but I want to look at transient bounds without any scaling. I don't want to multiply by n and so on. And I think your main result has everything that can be said, but can that be converted? For example, if I look at the simple 2Q system that you presented at the very beginning, can I say, so we know that there is state space collapse, and then the steady state distribution should be an exponential on the line. So now I'm interested in, for every time t, how far is my distribution from this exponential on the line? Actually, that is something I'm actively working on. So I'm curious if your result basically gives that as a corollary.
Suppose that you start at 0. After time t, my result will only tell you that you are at most square t away. So that's probably not very helpful.
I see. I see. I see. I see. But then you're able to get the steady state results by somehow killing that square root of t.
Yeah, but somehow there you need to start using a Lyapunov function and to argue that each time that your state becomes big, something brings it back.
I see.
Our results,
I see. Okay.
our results do not kind of capture that feature, the fact that 0 is an attractive point. We're not capitalizing on that.
I see. I see. Got it. Got it. Thanks. So my last question, suppose the service is also random, like in a load balancing system or even like a single server queue.
Yeah.
How far do these results carry over?
I haven't thought about it, but it should work the same way.
Okay.
That my guess or conjecture is that we can generalize to that case.
Okay. Okay. Thanks.
So let's stop the YouTube live
Who
and
has a question?
Zoom recording, and then anyone, please feel free to just ask questions.